Hi guys, we're having a look at some matrix arithmetic. We're reviewing it in this session, so fasten your seatbelts, get ready for some thrills and spills. Now, a matrix is a rectangular array of numbers. That is, it's got some rows and it's got some columns, okay? Two matrices A and B are equal when two very obvious things have to happen. Firstly, each has to have the same number of rows and columns. Secondly, they have to have the exact same element in each position. Okay, so if you look at that left-hand matrix, the left-hand matrix is identical to the right-hand matrix if A equals 3, B equals 6, C equals 5, and so on. Yeah? There it is, pretty obvious, yes? Next point. The size or dimension of a matrix is described by specifying the number of rows and the number of columns. This dimension is written as M by N, rows by columns. The dimensions of the following matrices in order are, right, 3 by 2, you get that? 3 rows, 2 columns. Yes, that's row by column, row by column, row by column, row by column. That's 3 by 2. That next one's a 1 row, 4 columns, yes. 3 by 3, a square one, that's called square when the number of rows equals the number of columns, and that last one is a 1 by 1. Doesn't even look like a matrix, but it is by definition a matrix with 1 row and 1 column. If we look at it, makes sense, doesn't it? Alright, now, addition will be defined for two matrices only if they have the same dimension. This is very true. The sum is found by adding the corresponding elements. Yes, do you get that? See, top left you'd have A plus E. Yes? And that's how it goes. Yep. Now, what would that be? Minus 2, that would give you, top right would be 8, bottom left would be 10, and bottom right would be 13, wouldn't it? Yes, good. Here's a minus 1. Come on, let's do it. What do you think? Top left, 1 minus negative 3 would be 1, plus 3 would be 4. 2 take away 6 would be minus 4, 3 take 7 would be minus 4, 4 take 9 is minus 5. Okay, to keep us alive and help us to thrive. This next bit, if A is an M by N matrix and K is a real number, then K times A is defined to be an M times N matrix whose elements are K times the corresponding elements of just A, right? Just multiply every single beastie in here by K and you'll be right. Now, so what would this get us, guys? That would get us a plus 2, top left, wouldn't it? Top right would be minus, bottom left be minus 12, top right would be minus 6, and bottom right would be minus 18. There you go. You get it? That's pretty easy. Yes. Now, if A is an M by N matrix and B is an N by R matrix, we're going to multiply them together now. The product of A times B is an M times R matrix whose entries are determined as follows. To find the entry in row I and column J of A times B, and by the way, the order matters. Did you know that? Just throw that one in for good measure. A times B is different from B times A, right? So just tuck that one away, it's very important. You single out the row I in matrix A and the column J in matrix B, and you multiply the corresponding entries from all of the entries in that row by all the entries in the column. That is row, the first element in the row by the first element of the column, times plus the second element of the row times the second element of the column, and so on till you get to the end of the row and column respectively. Okay, and then you add up the resulting, you add those entries up to get you a single entry in the new position of the multiplied matrix. Now, if that sounded gobbledygook, I'll show you, don't worry, I will show you. The product of A times B is defined only if the number of columns of A, this is really important, is the same as the number of rows in B. Now, I'll show you that in a minute. Right, now, do you see this? This has got, right, 2 rows, 3 columns, right? 2 by 3, right? 2 by 3. This is 3 rows, 2 columns. That's 3 by 2. Now, those middle numbers, I said 2 by 3. Note the second number there, 2 by 3 and 3 by 2. Those middle numbers, the 3 from the end of this dimension and the 3 from the start of this dimension have to be the same, the middle numbers. 2 by 3, 3 by 2, those 3's in the middle have to be equal if they are multipliable together, if you know what I mean. Yes, A is a 2 by 3 matrix, B is a 3 by 2 matrix, therefore A by, now this is also interesting, A by B is a 2 by 2. I'm going to explain that in a minute. The outside numbers of the two respective dimensions of A and B give you the dimension of the product. I'll explain that in a minute too. Now, A by B is that. Those numbers must be equal. Did you see how I've written that there? Those numbers must be equal. Otherwise, all bets are off. You can't multiply them. And these numbers here give you the dimension of the result of the product. Okay, so it's a 2 by 2 is the result of the product of A times B. Yes, right? A 2 by 2, that's the dimension of the product. But if these numbers, these middle numbers here, this one here, and this one here are not the same, you can't multiply them at all. Okay? Now, so what do? Well, okay, you multiply, say this is row 1, you multiply the entries in row 1 by the entries in column 1. Okay, so it'll be 2 times 4 plus 3 times 1 plus 4 times 0. That gets you, that's row 1, column 1, gets you entry at row 1, column 1. Okay, in the new matrix. Do you see that? Now, if we were going to multiply this row 2 by column 1, it would be 5 times 4 plus 6 times 1 plus 7 times 0. That would be row 2, column 1 would get you the entry at position row 2, column 1 in the new matrix. You see? That's how you do that. Do you get that? That's how you do it. And then you just simplify here. Now I'm going to show you in the next screen step-by-step multiplication of matrices, right? Now if we're going to multiply those two matrices together, here I go, explaining it to you in words of a syllable, or perhaps 2 syllables, or 3, but very simply, as simple as I can make it. First of all, you check for compatibility. So A is a 2 by 3, B is a 3 by 2, so those middle numbers, the 3's, that means they're compatible. Okay? Yes, A is a 2 by 3, B is a 3 by 2. So therefore, yes, look, these numbers here, that 3 there and that 3 there, they're the same, therefore the matrices are compatible. Okay, middle numbers are equal. So that means A times B is possible. Now you check the dimensions of A times B with the outside numbers. It's going to be a 2 by 2, right? It's going to be a 2 by 2 matrix, okay? Right, having done that, now we can proceed with the actual multiplication. You multiply each row in A by each column in B to produce a single entry in the respective positions of A times B, knowing that you're going to get a 2 by 2 matrix result. Now, okay, so that's what I'm saying there. Row 1 in column A times column 1 in, what did I say? Row 1 in matrix A times column 1 in matrix B produces entry at row 1, column 1 in A times B. Now, have a look at this. Look, I'll show you. I use these lines to sort of help me get my head around what's going on here. Look, now, that's going to be the 2 by 2 template of the matrix that I'm going to produce, right? Now, watch this. If I multiply that row by that column, see how that kind of intersects at a top left kind of position? Well, that's where you're going to get your entry in the new matrix. So 2 times 4 plus 3 times 1 plus 4 times 0 all adds up and goes into that position there. Okay? See? Now let's do another one. This top row in the left-hand matrix times the second column in the right-hand matrix. See how they intersect at a kind of like a top-right kind of orientation there? Well, that's what you're going to get there. That's going to be the result of doing that multiplication. Now you're getting the idea, aren't you? So what about row 2, column 1? Row 2, column 1 gets you a kind of like a bottom left orientation, so that the result of doing that multiplication is going to go there. Okay, now last but not least, we'll get row 2, column 2, and that's a bottom right orientation where they intersect, so that's going to get you an entry there. Okay, now let's actually do it now. There it goes. There's the next one, there's the next one, there's the next one. Right? If you follow along, if you pause the video, you'll see that's how you do it. You'll see that that's right. Yes? Okay, now if you simplify that, it'll come to, that apparently is 11, top left, 18, top right, 26, bottom left, and 33, bottom right. Yes? Yeah, see, that's how you do them. Now, what have I got here for you? The identity, oh yes, the dear old identity matrix. The identity matrix for the family of n by n, in other words, see that's an n and that's an n, not n by n, but n by n, in other words, square matrices, is the matrix with ones in the top left to bottom right diagonal and zeros in all other positions. This is denoted by I, the identity matrix, right? Now here's some examples. For a square 2 by 2, that would be the identity matrix, right? They have to be square ones. Yes. For a square 3 by 3, that's what the identity matrix would be, right? Get that? This only applies to square matrices, yes? Now, what have I got here for you? If A and B are square matrices of the same dimension, B and A times B equals B times A equals I. That's what a way to explain that. Well, then A is said to be the inverse of B. In other words, a matrix multiplied by its inverse gives you the identity matrix, guys. That's what you need to know. A matrix multiplied by its inverse gives you the identity matrix. That's what I want you to know, okay? Now, the inverse of A is denoted by that little thingy there, okay? Looks like A to the minus 1, but it's the inverse of A. Now, what you do here is this is how you get the inverse. You reverse the A and the D, and you minus the B and minus the C, and you basically divide every entry by what's called the determinant. The determinant is AD minus BC, okay? Right? If you've got to put these symbols in the right positions, A to B to C to D, right? Going across the page like the way you'd read a book. A to B to C to D. Now it's AD minus BC. So every one of these entries, once you reverse the A and the D, and you negative the B and the C, then you've got this, and you divide every single one of them by the determinant, you've got the inverse. That beastly looking thing is the inverse of A. Okay, that's how it goes. Now, I think I've I've explained it all here for you so you can have a look. To find the inverse of A, yes, you find the determinant, which is AD minus BC. That's that one, minus that one, right? Now you reverse the A and the D entries, take the negative of the B and the C entries, and then you basically, whatever you're left with in that square bracket, you divide the whole matrix by the determinant, and that's your inverse. That is your inverse, yes? Some might say perverse. It looks like it, doesn't it? It's so complicated, but it's just the inverse, right? Right, what's this? A square matrix is said to be regular. Now, this is important. A square matrix is said to be regular if its inverse exists. Those square matrices which do not have an inverse are called singular matrices, and the determinant of a singular matrix is 0. So why don't they have inverses? Because you remember, to get the inverse, you've got to go 1 over the determinant times the fiddled around with entries in that square matrix. Now, you can't go dividing by 0, so a singular matrix, it has a determinant of 0, and therefore to get the inverse you'd have to divide 1 by 0 outside the entries, which you can't do. Okay? That's the deal. So for square matrices, I've got A equals that. If the determinant of A equals 0, A is a singular, A is called singular, and it has no inverse because you can't divide by 0, okay? If the determinant of A is not equal to 0, then A is regular and does have an inverse. Those terms are just definitional. Singular means determinant equals 0 and there's no inverse. Regular means determinant does not equal to 0 and it does have an inverse, right? So now, this is the deal. If the ratio of A compared to B is the same as the ratio of C compared to D, that's the situation you get in order to have a determinant equal to 0. If that's the case, if you like, if you wrote it in mathematical terms, if A over B equals C over D, or if A is to B is the same as C is to D, they're in the same ratio, then AD minus BC will equal 0. That means the determinant will be 0 and is a singular matrix, right? That's basically what you need to do to have a singular matrix. Now, you have a look at that case there. I've got exactly the same ratio. See, the ratio of A is to B, that's a 1 is to 2. The ratio of C is to D is a 1 is to 2. Now, I'll tell you that is a singular matrix, guys, because the determinant is, right, is 2 times 6 minus 3 times 4, which equals 0. I told you, didn't I? So that's a singular. No inverse. What's this one? For B, now that's that one is not, that's a regular, because AD minus BC is not equal to 0, because the ratio of A is to B is not the same as the ratio of C is to D. Okay? So that comes to 2 times 6 minus negative 1 times 3, which will be 12 plus 3, which is 15. So therefore the inverse of B would be 1 over 15 times reverse the 6 and the 2 and minus the entries of the 1 and the 3, so the minus 1 becomes plus 1 and the plus 3 becomes minus 3, and that's your inverse, guys. That's it. Okay, now here's an example for us. Let's go. Now we've got to work out, this is the matrix we're dealing with here. Just have a quick squeeze. Is the ratio of that compared to that the same as the ratio of that compared to that? No. So therefore it's not a singular matrix, it's got an inverse. So the determinant of A, then the inverse of A, then X, matrix X if A times X equals that, and matrix Y if Y times A. See how the order of the multiplication has been changed? So A times something equals this, and then something times A equals that. Now, remember earlier in the video I said that the order matters? Well, we are going to prove that, having a look at the results of C and D. But let's first do A. A, the determinant of matrix capital A. So that'll be, what's the determinant? AD minus BC, so it's 3 6's minus 2 1's, which is 18 minus 2, which will get us 16. Yes? Number B, now the inverse of A. So, okay, now, remember what I said to get the inverse? It's 1 over 16, okay, times, fiddle with those numbers inside there. 1 over 16 times reverse the A and the D, and just negative the B and the C in situ where they normally would be, just make them the negative of whatever they are. Okay, that's the inverse of A, right? Well, we've done A and B, no problem. Now, here comes C. Watch this. This is where we use the inverse to create an identity matrix. Now, watch this, watch this. We've got A times X equals that. Now, therefore, what we do is we try to neutralise that A there by multiplying by its inverse in front of it, because remember I said if you have a matrix multiplied by its inverse, or an inverse of a matrix multiplied by the matrix, you'll just get the identity matrix. Yes, that's what we're trying to do. So we're multiplying both sides in front, because remember the order matters, in front by the inverse of A. So in front here, in front there, right? Now that basically, as I said to you, doing that creates the identity matrix, right? And I is the identity matrix, which is just like the same as a 1 in normal maths or algebra. So we know that IX, which is what A inverse times A equals, is equal to that. But IX is just like a 1 in matrix land. So I times X is just X. That's why we're doing it, because we just want to get X. We're solving it for X. That's what we want. Remember, look, we're asked for X. See? That's why we do this. So therefore X is the inverse of A times that matrix there, okay? This matrix here they have given us, yes? So we already worked out the inverse of A in part B, didn't we? So there we're going to sub for that, and now we just got to do the old cruncheroonie, okay? Do the old multiplication. Now, okay, so I've just done it there for you. You can pause the video and have a go if you like. Come back and see if you get the same as me. Yes? Alright, well I'm doing it now. There she be, Jim. And what's that? Goodness. Well, you'll have to believe me. You better pause the video and have a look and do it yourself, if you don't want to believe me. There it is, okay? So therefore, now if I look, I think I can just divide, I can just put this 1 over 16, express that, whatever these numbers are, divided by 16. So that'll be a 1, that'll be a 1, that'll be a 2, that'll be a 0, so that's going to be my answer. So that is, now, that is x, matrix x, if A times x gives me this. Now, over here, if the order of the multiplication is done is different, if the order of the multiplication didn't matter, then y multiplied by, well, a is multiplied after the y, or y is in front of the a, whereas the x was behind the a over here. If it didn't matter the order of multiplication, then basically you'd get the same, y in part D would come out to be the same as x was in part C, but it doesn't come out that, as I'll show you in a moment. So the order of multiplication matters in matrices, right? You watch. Now for this beastly little piece of work, what we've got to do there is we've got to say, how are we going to work out y? Why? Yes, I know. Well, we can but try to work out y. So what I'm going to do is I'm going to multiply behind. I'm going to multiply y times capital A times the inverse of capital A. Okay, and then I'll do the same thing by multiplying the second position of multiplication over here will be the inverse of A, right? So we're multiplying by capital A inverse on the right-hand side of each of these terms, on either side of the equal sign. I'll show you. See, what's that? See, that's what I'm doing. Now, yes, I know, clever, eh? Well, I didn't think of it. Someone showed me, so I have to own up. This is, that there is just going to give me the identity matrix, which is just going to be y, isn't it? It is. So let's then see what this comes out to be. There it is, right? There it is. Now, that looks pretty revolting, but it's not so bad if you just plug away and just keep your head and don't be an algebra hero by doing too many steps at once. You'll be fine. There it goes, there it goes, there it goes. Now that simplifies to that, and that, and that, and that, and now I think 24 over 16, they're multiples of 8, aren't they? So it's 3 over 2. That's a multiple of 8, and of course they are both 8s, 1 plus 1 minus. So we can just express that as that, that, and that. Now that is a very different answer to that one there, right? So see, have I proven my point? That's what y is. Y is different from x. So if the order didn't matter, then that y would come out to be the same as that x, but it comes out to be different. So the order matters, right? Do you get that? The order matters. That's the end, and you're a star, huzzah, and you'll go far as long as you practice so that you understand your matrices, because they're quite different little beasties from anything you've ever come across before, and practice always makes perfect. So go ahead and do that, and we'll catch you in the next very exciting video, which looks at solutions of two variable simultaneous equations using matrices, okay? So watch out for that one. We'll see you next time. Bye.